Okay, so one of the things we need to do is be able to recognize when we see a limit problem, like some of these three that are listed down here, and that most often when we see one of these from this point on, we're not going to be asked really to find the limit analytically, like factoring and canceling or multiplying by a conjugate or something like that. We need to see this limit as some representation of the derivative of some function, sometimes at a particular value of x, sometimes not. So if you go back to our chapter 1 stuff, when we learned about the definition of the derivative, and we had the literal definition, the limit as h goes to 0 of f of x plus h minus f of x over h, and what that yielded was the derivative of f of x, which is some function of x, at any x value. And what it's going to do is it's going to give you something in terms of x that's going to predict the slope of this function f of x that's written right here. Then we had the alternate form of the derivative, which was valid or useful for determining the slope of f of x at a particular x value called x equals c. And the answer in these kind of problems is always going to be a numeric value. It's going to be a number. And then lastly, we had what I call the hybrid, which kind of has this look to it with the limit as h goes to 0. But rather than having any x here, they have a specific x value, the c value that you saw up here. So that has the look of f of c plus h minus f of c over h. So I call it the hybrid because it kind of has this look of f of x plus h minus f of x, only it has a particular c value that's being, this particular x value called c, that we're finding the slope at that particular point. So I've got three limit problems here, and what I want to do is recognize that when we see one of these, we say, okay, well, let's see, is it possibly the derivative of some function? And if so, let's approach it that way instead of having to figure out, some sort of analytic technique to solve it. Because we can just take the derivative of the function, and then if it's at a particular value of c, we just plug that number in and we're done. So this first one, x is approaching a particular value of pi over 3, x approaching pi over 3, x minus pi over 3, x approaching c, x minus c. We definitely see that this first one has to be one of these alternate forms. It's going to be the derivative of some function evaluated at x equals pi over 3. So for number 1 here, we say, okay, well, I know it's this alternate form right here for number 1. And we can see that f of x is the function that's in the upper left-hand corner here. It's sine squared of x. So we identify f of x is sine squared of x. And then we say, okay, what's our c value? And in this particular case, it looks like x is approaching pi over 3. So x approaches c, x approaches pi over 3. So our job is, okay, all we need to do is take the derivative of this function and plug in pi over 3, and we put that down as our answer and we walk away and we're done. So let's think about what f prime would be. So if f of x is sine squared of x, we have to realize, hey, that's a function, sine of x, that's being functioned, it's being squared. So we need a chain rule. So we're going to take the derivative of the outer function, the squaring. So we bring the 2 down in front, drop the power to the first power, and I guess I could write a little 1 there. And then we go back and take the derivative of what's inside, which is the sine function. The derivative of sine function is cosine function. So there's the formula for the derivative at any x, but we want it at x equals c. So we plug in pi over 3, and we get 2 times the sine of pi over 3 times the cosine of pi over 3. And then we just know our unit circle well enough to know that the sine of pi over 3 is root 3 over 2, and the cosine of pi over 3 is 1/2. These guys can kill each other, and we're left with root 3 over 2. And we simply write the answer to this limit is root 3 over 2. So we never took the limit per se. We just recognized that this limit is asking us for the derivative of sine squared of x evaluated at pi over 3. So we move on to our next example here. And for our next example, we've got h going to 0 for both the second and third one. So we know we're talking about these two guys. But we notice in number 2, there's no specific x value mentioned anywhere. This is x plus h minus 2 root of x plus, or minus 2 times the quantity x plus h, all being square rooted. And then we've got minus the square root of x squared minus 2x. So it's like, this certainly looks a whole lot like this, where this guy right here is our function. So all we have to do is, for this type, when you see the x plus h's and the x plus h's, you say, oh, this is the definition of the derivative. So we identify the function in this case. Let's maybe change colors for this one. Number 2 we'll do in red. So f of x here is just whatever this function is here after the subtraction, and appears to be root of x squared minus 2x. So I'm going to write that as x squared minus 2x to the 1/2 power. So all I need to do is figure out what the derivative is. Because remember, the answer in these kind of problems is just going to be some function in terms of x. there's no x value to plug in. So I bring the 1/2 down in front, x squared minus 2x, drop the power by 1, and then take the derivative of what's inside, which is 2x minus 2. Now I rigged this one a little bit because this 1/2 here can multiply by 2x minus 2 and become simply x minus 1. So I'm going to get x squared minus 2x to the negative 1/2 multiplied by x minus 1. And I guess I can rewrite that as x minus 1 over x squared minus 2x. And rather than writing the 1/2 power, I will put a square root symbol there. So let's call that square root of x squared minus 2x. And there's our answer. So x minus 1 over the square root of x squared minus 2x. So again, we didn't do any analytic work to figure out what the limit was. We just recognized it's asking us for the derivative. So we've got one more example here. H is heading towards 0, so we know it's one of these two guys. But because we have a particular x value here, pi over 6 rather, c plus h, pi over 6 plus h, c plus h, pi over 6 plus h. So I'm pretty sure, if nothing else, that for this one we can start by saying, hey, I know that c is pi over 6. Now the little technique we used earlier in the year we can certainly apply here now. So we kind of say, I know the function is going to come from this expression right there. So we look at that and we say, okay, that's f of x plus, I'm sorry, that's f of c plus h. So since c is a particular x value, I'm going to take this c value here and replace it with just a regular x. So I can say, all right, f of x is going to be tangent squared of, instead of pi over 6, I'm going to write x plus h. So all I've done is taken out pi over 6 and replaced it with x because it represents an x value. And then I say, all right, well, what I want is f of x, not f of x plus h. So I can just erase that plus h portion, and I can see now that f of x is tangent squared of x. So just like we did in this first problem up here, we have to first find the derivative and then go plug in our specific c value. So let's go do that. The derivative is going to be, we're going to take the 2 down in front and make it 2 tangent of x, which is now being raised to the first power. And then we take the derivative of tangent, which is secant squared of x. So that's the derivative. We just have to plug in pi over 6 now. So we're going to get 2 times the tangent of pi over 6 times the secant squared of pi over 6. And now we go evaluate those. So for pi over 6, you should know your circle well enough to know pi over 6 is here. Got a 1, a root 3, and a 2. So tangent of pi over 6 is 1 over root 3. And the secant of pi over 6 is 2 over root 3. But that's being squared. And that squaring will square the numerator and the denominator. So we've got 2 times 1 over root 3 times 4 over regular 3, because the root 3 is being squared, which to me looks like 8 over 3 root 3. And I'd be happy if you just left it just like that. Don't worry about a radical in the denom. So there's our expression, and the limit is 8 over 3 root 3. So there you go. Good sample of a few different problems that you could see where you're being asked for a limit, but really you just need to recognize a function and when appropriate, the x value that we're looking for the derivative at.